Line I1, Learning Task 2, Determine Protective Device Requirements. Okay, so our Canadian Electrical Code has a number of different sections that we're aware of, grounding and bonding and general requirements, installations, etc. We're going to have one section that's going to be referred to as Section 14. We often refer to this as PNC, or Protection and Control. And Section 14 is going to go and specify when I need to go and have a protective device. And generally speaking, it's usually going to be anytime that I've got an ungrounded line. Those protective devices that are going to be listed inside the code could be fuses, they could be circuit breakers. There's a bunch of finer rules that are going to go and talk about them. But ultimately, what we need to have is some form of protection. And what we want to have is we want to go and have protection that is going to be able to respond in the event of any sort of a fault. What we have under a fault is we have the generation of what's called fault current. And I know that the term fault current sounds a little bit scary to us. We don't like the idea of fault current because it could be a big value, and it oftentimes will be. However, we do want to generate a large amount of current when we have a fault, so that we'll be able to actually activate the circuit breakers. Remember that circuit breakers and fuses are going to go and be thermal or thermomagnetic devices. They need to have a bunch of current through them to go and produce heat or to go and produce overcurrents. Let's just examine what happens on an actual system. We know that we've got a supply transformer. It's not shown over here. It's just going to be a standard 3-wire system. We will draw this thing out like that. We've got our transformer. We're going to go and have line 1 of that transformer that is going to go and connect to one of my lines. We are going to go and have line 2 of that transformer. I'm going to draw it in blue just so that it's easier to see. This is going to connect to the other line. And we are going to go and have my neutral, which is going to go and connect to my neutral that I'm going to have. That all gets carried down, gets carried through our meter base, and from our meter base, we feed those lines into our actual panel. We'll just identify those lines here. We'll make that one the red line. We will make this one here the blue line. They just go all the way up and through to our weatherhead that we see up top there. Anytime that we have got a fault, what we will see is we are going to see the generation of large amounts of current due to low resistance. We need to have that low resistance. So looking at this over here, we've got a circuit breaker. We're going to identify this as being on the red line. We don't have them identified all the way through, but we will say that this is going to be on the red line, the line 1 that I'm going to have. If this thing were to go and fault to the metal of the box itself, what's then going to happen is that I'm going to have a complete circuit. So I can say that I've got current that is going to be coming in through here, through my bus, through down here, and it is going to go all the way up to there. So that's going to be my incoming current. What happens then is that current wants to go and return to the supply. It does not want to go to ground or anywhere else. It wants to go and use the bonded system to go and return. So what it will do now is it's going to go and track back through the metal of the box, up the conduit nipple we see over there, through the back plane of the panel, where it's then going to go onto my ground lug of this panel. From the ground lug of the panel, it's going to travel along the bond conductor back up to where it was bonded into the bond lugs on the other panel. From there, it's going to go and travel up the case of the panel, and then it's going to go up that little bonding strap that goes between your neutral and your bus bar. From there, it is going to go and return to the neutral, and then it can utilize that neutral to travel all the way back up to the transformer to complete a circuit, right? This is what we always want to go and see, is a complete circuit. You can follow the yellow. The yellow is going to be the current that we are feeding in from my line 1. The green is going to be the current that's traveling back along my bonding system all the way back up to it. Obviously, this could be a very large value because my value of resistance of all this bonded together metal is going to be very low. We stick 120 volts, and if we stick that over top of 1 ohm of resistance, we would see that we would have 120 amps, right? That's going to go and be developed out of here. So we need to size things according to the amount of fault current that will flow. Note, this is not included in the path. This is my actual ground wire. We'll talk about that inside of grounding and bonding a bit more, but it's not included. The current doesn't flow along there. So I need to go and size all these other components, particularly things like this, that bond wire that's going to be going through my PVC conduit from my main panel over to my sub panel. I want to make sure that all of those are going to be sized to be able to carry large amounts of current. Two main types of faults that we have are going to be either what we had in here. This is going to be a fault from a hotline down to the box, which is going to go and carry us back. We call that a line to ground fault, or a phase to ground fault, from one of our phases to the actual ground. The other type that we can have is going to go and be a line to line fault. And a line to line fault is simply going to be where I'm going to have current that is going to be, it's kind of hard to see over top of that one. We'll try this one again, but maybe we'll start up here. We'll go through the blue conductor this time, delivered through here and back down through my red conductor. And it could be that I've got two lines over here, that this line is connecting to the box and that this line over here is going to be connecting to the box as well. As a result of that, we are going to go and have, large amounts of current that are going to be able to once again flow, because now we're doubling up our value of line voltage. Anytime that we get a phase-to-phase fault or a line-to-line fault, we have to always worry about how much current could this transformer potentially go and deliver. And we've got short-circuit current ratings. Now, we've done short-circuit current calculations before. They're basically going to go and be by I secondary of the transformer. There's a primary to this transformer. It's going to be a high voltage one supplied by BC Hydro. We're just ignoring that. But my I secondary divided by my percent Z. I know the formula that's inside of your binder is a little bit different. They're multiplying it by 0.01 and stuff like that. It doesn't matter how you decide to go and write percent Z. You have to put it in as a decimal thing. In other words, if this could go and supply a maximum of 200 amps as its secondary rated current, but if it had a 3% impedance, 3% Z, what I would have to do is I would have to take 200 amps and divide it by 3%. 200 divided by 0.03. That's going to be my 3%. And then that altogether is going to go and kick out my total value. Let's punch that in here. 200 divided by 0.03 gets me to a value of 6,666.7 kilo amps that we are going to go and have. 6,667 amps, or 6.7 kA that we would have delivered off of this. We need to size it for that one. They give you right below all of those calculations a sample. Do try to figure out that sample component itself. All right, let's talk about series ratings. Series ratings are going to happen anytime that us doing a fully rated system is going to be too large. Let's say that for this example over here, that we had something that was going to be rated as a 400 amp service. You can get 400 amp services. The metering and stuff does look different than this, I get that, but we're just using it as an example over here. 400 amp service, same percent impedance, which would mean that we are going to go and have approximately 19.8, I think it is, something like that, 19-ish kilo amps of available fault current that we would have. Every component along the line could be fully rated. In other words, I can make sure that this breaker, these breakers, these breakers, this breaker was all rated to be able to interrupt 19,000 amps. However, that could get expensive because we know that most of our standard breaker ratings are going to go and be no more than 10,000. So I can go and have a different type of system. Instead of having fully rated where everything can interrupt that, I'm going to go and have series rating where I'm going to have cascading values. With this one over here, this one has to. We always need to have at least something on there that can interrupt the full one. But I'm going to go and have one over here that's going to go and interrupt. This one might be 20 kA that it can go and interrupt. And then these breakers inside of here, might be 10 kA. And then this one over here could be a 10 kA as well. And then this one over here, all the rest of these could all be 10 kAs as well. What this would allow us to do is we can still safely use this because we know that there is going to be something upstream that is going to go and be able to deal with the maximum available fault current. The overcurrent devices that I have inside of here, so the main breaker and the other smaller ones, are going to go and operate at the same time. And as long as one of them is going to be rated for the actual full kiloamps, then we're going to be fine. What we would not want to have is we would not want to have something where we're going to have, 10,000 kiloamps on this one. If I had this over here as 10 kA, it wouldn't be able to go and interrupt. Your incoming is always going to have the biggest interruption. Everything past that is going to be able to go and work downstream. Now, for me to have a series rated system, generally speaking, they're going to be engineered. In a lot of cases, if you, once again, stick with a manufacturer's entire product line, if I'm dealing with something and it's all going to be square D over here, then this, in a lot of cases, is already going to come pre-series rated for me. But you have to be careful. As soon as you start fooling around with changing different types of panels and breakers and suppliers, there's always that chance that that series rating is no longer going to go and work out. All right, that is it for this one. Calculate your fault current. Do that little example that's right below their calculations that they have over there. Make sure you understand what it is and the difference between your phase-to-phase and phase-to-ground